Imagine you're standing inside a ship, not a plane, not a submarine, a spacecraft, the most advanced machine humanity has ever built. Every wire, every bolt, every ounce of fuel was designed for one mission: to leave the solar system and reach the nearest star, Alpha Centauri, the closest neighbor we have in this entire galaxy. You strap in, the engines ignite, the Earth shrinks behind you. You feel it, that primal electric rush of leaving everything behind. You are going where no human has ever gone, and you will never, ever arrive, because the star you're heading toward is 4.37 light years away. And at the fastest speed we can currently launch anything into space, it would take over 73,000 years to get there. That is not a typo. 73,000 years. Let that satisfy you for a moment. Picture it. 73,000 years ago, modern humans were painting caves with their hands. Mammoths walked the frozen plains of Europe. Language barely existed. Writing wouldn't be invented for another 60,000 years. That's how long this trip would take. You wouldn't arrive. Your children wouldn't arrive. Your civilization might not even survive long enough to remember the ship existed. But here's the thing. We could actually launch it today, right now. We have the technology to build a spacecraft and aim it at Alpha Centauri. It's not science fiction, it's physics, it's engineering, it's real, and that's what makes this so terrifying. Because the problem was never about building the ship. The problem is everything that happens after you press the button. Let's start with the speed. The fastest object humanity has ever launched into space is the Parker Solar Probe. It screams through the void at roughly 635,000 kilometers per hour. That's fast enough to fly from New York to Tokyo in under a minute. Incomprehensibly fast, and it is nowhere near fast enough. At that speed, reaching Alpha Centauri would still take about 6,300 years. So engineers have imagined other options: ion propulsion, nuclear pulse engines, light sails pushed by ground-based lasers. The breakthrough Starshot project proposed sending a tiny probe the size of a postage stamp at 20% the speed of light. That would cut the trip down to about 20 years. Beautiful, right? Elegant, except it only works for a chip, not for a crew. Not for a living, breathing human being inside a vessel that needs air, water, food, gravity, and radiation shielding for decades, or centuries, or millennia. And this is where things change. Because the moment you put people on that ship, every single law of physics becomes your enemy. The first thing that kills you is the emptiness, not emotionally, physically. Interstellar space is the most vacant environment in the known universe. Between stars, there is almost nothing. No gas stations, no asteroids to mine, no planets to land on. If something breaks, a water recycler, an oxygen generator, a hull panel, there is no rescue, no resupply. You are further from help than any human being has ever been, and with every passing second, you're getting further. Voyager 1, our most distant probe, has been traveling since 1977 and hasn't even left the influence of our sun's magnetic field in any meaningful way. And it's heading in the wrong direction for Alpha Centauri. It will drift through interstellar darkness for 40,000 years before it even passes close to another star. And that star isn't Alpha Centauri either. It's just wandering, alone, in nothing. But it gets worse because even that nothing can kill you. Interstellar space is flooded with cosmic radiation, high-energy particles blasted out from supernovae, black holes, and the cores of distant galaxies. On Earth, you're shielded by the atmosphere and the planet's magnetic field. On the International Space Station, astronauts receive roughly 10 times the radiation dose of someone on the ground, and they're only up there for 6 months. On a ship hurtling through open space for centuries, with no planetary magnetosphere to hide behind, your crew would be bathed in a constant stream of particles that shred DNA. Cancer rates would skyrocket, mutations would accumulate generation after generation. Children born on the ship would be weaker than their parents, their children weaker still. The very biology of the crew would begin to unravel, and there's no drug, no shield, no technology we currently have that fully solves this. You can bury the living quarters behind meters of water or regolith. You can line walls with polyethylene. But cosmic rays, especially the heavy nuclei called HCE particles, punch through almost everything. They pass through your skull and leave microscopic trails of destruction in your brain tissue. NASA calls them the single greatest obstacle to deep space travel, and that's just for a trip to Mars, which takes 7 months, not 73,000 years. But that's not even the worst part, because radiation is at least a danger you can see coming. The real nightmare is what you can't predict. Over 73,000 years of travel, the ship itself begins to die. Metals fatigue, seals degrade, electronics fail. Every component on that vessel has a lifespan, and no material human beings have ever manufactured is meant to last 700 centuries. Think about the oldest human-made structures still standing. The pyramids of Giza are about 4,500 years old, and they're stone blocks sitting in a desert. No moving parts, no pressure differentials, no thermal cycling. Now imagine a spacecraft, a pressurized, mechanically complex, electrically dependent ecosystem surviving 16 times longer than the pyramids, in a vacuum, while being bombarded by radiation, while supporting a living population. And here's the problem no one talks about. It's not the ship that's the hardest part, it's the people. How do you maintain a functioning human society for 73,000 years? Think about what's happened in just the last 5,000. Empires rose and collapsed. Languages were born and went extinct. Entire religions formed, spread, and vanished. On a generation ship, you're asking a population to maintain a mission, a single, unwavering purpose, for longer than all of recorded human history. Psychologists call this the mission drift problem. After enough generations, the original goal becomes mythology. Your great-great-great-grandchildren 100 times over won't feel connected to Earth. They won't understand why they're on the ship. They might not believe Alpha Centauri is real. They might form new religions, new governments, new wars, all inside a metal cylinder floating through nothing. The ship stops being a vessel and becomes a world, and worlds have a way of tearing themselves apart. And even if, by some miracle, the society holds, and the ship holds, and the biology holds, there's one more danger that makes all the others feel small: the destination itself. Alpha Centauri is not one star. It's a system, 3 stars locked in a gravitational dance. Alpha Centauri A and B orbit each other, and a smaller red dwarf called Proxima Centauri orbits them both from a vast distance. In 2016, astronomers discovered a planet orbiting Proxima Centauri, Proxima B, sitting in what they called the habitable zone. The media celebrated, a second Earth, they said, but the reality is brutal. Proxima Centauri is a flare star. It erupts with violent bursts of X-rays and ultraviolet radiation, sometimes thousands of times more intense than anything our sun produces. In 2018, a superflare was detected that was so powerful it would have stripped the atmosphere off any planet in its path. If Proxima B ever had an atmosphere, it's probably gone. If it ever had water, it's been blasted into space. You would arrive after 73,000 years of survival, of sacrifice, of holding everything together, and you would find a scorched rock bathed in radiation, orbiting a star that is actively trying to sterilize everything around it. But now imagine something even more haunting. Imagine the ship launches today. It crawls out of the solar system at the best speed we can manage. 1,000 years pass, 2,000, 10,000, and then 40,000 years into the journey, a faster ship, built with technology that didn't exist when you left, passes you. It arrives at Alpha Centauri decades before you do. It colonizes the system, builds cities, grows old. And when your ancient crumbling vessel finally limps into orbit after 73,000 years, you're not pioneers, you're relics. Fossils from a forgotten age, arriving at a place that's already moved on without you. This is called the weight calculation, and it's a real mathematical argument against launching too soon. If technology improves at even a modest rate, any ship launched today will be overtaken by a faster ship launched later. So the optimal time to leave is never now. It's always tomorrow, and tomorrow never comes. This is the cruel paradox of interstellar travel. The stars are close enough to see, close enough to study, close enough to dream about, but they are not close enough to reach, not with bodies that age, machines that break, and societies that fracture. We could launch a ship to Alpha Centauri today. The math works, the engineering works, but no one alive would see it arrive. No one they've ever known would see it arrive. The entire history of human civilization